Hello, this is Samuel Anderson going through Tsiolkovsky's equation as shown currently. Delta V is or change in rocket velocity is equal to the velocity of the exhaust of the rocket times the natural logarithm of initial mass over final mass. Will be I will be going through why that is using Newton's second law, which as written or not shown yet, but I'm struggling with the computer at the moment. But many people have seen force is equal to mass times acceleration. That is one version of it where mass would be constant with respect to time. The issue is with rockets that mass changes over time, and that's how you get force going in a certain direction. So force is actually equal to the derivative of momentum with respect to time, or mom or force is equal to momentum change with respect to time. And this is equal to the derivative of mass times acceleration with respect to time. And when m is constant, or mass is constant in whatever object, doesn't matter, then this is equal to mass times the derivative of acceleration with respect to time. And you end, or sorry, velocity, mv, my bad. So you get mdv dt, which is equal to mass times acceleration. And this is the formula you see normally. However, rockets mass changes over time, so there's several extra steps. So using the fact that one force is equal to one momentum change with respect to time, then a sum of forces will be equal to a sum of momentum change, right? This could also be written as a sum of forces, and there are several forces acting upon a rocket. This will be equal. There are two important momentum changes, that being that of the rocket and that of the fuel. So this is equal to, call it m rocket, a rocket over dt. And I'm taking out the sum because this is the sum, okay? Times the mass of the fuel. I said a again. Velocity of the rocket times the velocity of the fuel, dt, right? And using the fact that there is a conservation of momentum, or momentum does not change with respect to time because it's constant, then the derivative is equal to 0. And so this entire thing, the derivative of this will equal 0. So scrolling down and using the product rule for mass and velocity, we would obtain some giant mess, but I will go through that. So we have the derivative of m rocket v rocket with respect to time is equal to the rate of change of the mass of the rocket times the velocity of the rocket. This is the product rule right here that I'm using, times the velocity change of the rocket with respect to time times the mass of the rocket. I'm talking about the rocket hull as itself, or the dry mass of the rocket, the part that does not change. The fuel is what changes. The fuel mass changes. The entire point of the rocket is to get the velocity to change because we want the rocket to go somewhere. and the mass of the rocket will not change with respect to time. So this right here is equal to 0, and this right here will actually change. It's not going to be equal to 0. So the derivative of the momentum of the fuel, m fuel v fuel, is going to be done very similarly. We have dm fuel dt times the velocity of the fuel plus the derivative of the velocity of the fuel with respect to time times the mass of the fuel. And in similar fashion, we want the mass of the fuel to change. We want the fuel to leave the rocket, and the mass in the rocket will change. So we want this, and we do not want to worry about the change in velocity of the fuel. We want it to be roughly constant, and it is with liquid rockets. So we can ignore this, and this is also equal to 0. And so we obtain overall, both of these are added together. We obtain that the change of the sum of the momentums is going to be 0. And that's going to be equal to dVr mr. This is dVr dt times mr plus dm fuel dt, velocity of the fuel. And if this is equal to 0, then one of these two things should be equal to, or should be the negative opposite of the other. So dVr dt mr is going to be equal to negative dm fuel dt v fuel. And this hinges on the fact that momentum change with respect to time is 0. This is conservation of energy and matter and momentum, all very similar. So we are going to do some integration, and remember that the integral of something over a variable, call it t, is going to be equal to ln of t. And if you remember, we obtain some constant times the logarithm where mass is changing. Mass is the thing on the inside of the integral, so that'll be the thing that's changing, is going to be the mass of the fuel, right? So we get the change in the velocity of the rocket, which, if you remember, delta V is what we're looking for. So keep the change of velocity of the rocket on one side. Going to get negative velocity of the fuel times the velocity, let's see, derivative m fuel dt over m. And if we integrate both sides, and the velocity of the fuel should be constant, we don't have to worry about that. That's constant we multiply by. Then we would obtain, using the fundamental theorem of calculus, that the integral of a derivative is going to be the velocity of at the final time t, call that v final, minus v initial. This can just be written as delta v as well, where the change in velocity of the rocket, net change rather, we would get negative v of the fuel, or this is the velocity of the exhaust. And this integral right here, dmv, will be equal to the natural logarithm, let's see, we would get the natural logarithm of mass evaluated at the initial and final time, t. Or delta V is equal to negative velocity of the exhaust times the logarithm, the natural log, final, minus the initial logarithm, or the logarithm of the initial mass, right? I should put my m's in there too. So we obtain negative V, call it V exhaust. We factor out this negative and we invert the two sides. We get, and then we take the fact that these are logarithms, and subtracting a logarithm is the same as dividing by one thing on the inside. We would obtain the the velocity of exhaust times the natural logarithm of the what is positive. Here we have mass 0, or initial mass, and we have mass final, mass F is being subtracted. So this would be the divisor, final mass. That's how Tsiolkovsky's equation is obtained.